Today, we are going to be taking a look at a relatively new paper that was submitted to iClear 2022. Funnily enough, it was rejected, but we're still taking a look because it actually has this really interesting idea, this new phenomena that they point out called decaying plasticity. This decaying plasticity, I'll give you a short sneak peek before we actually jump into the paper, is this idea that when you're using backpropagation in continual learning, and continual learning, some people also like to use the term lifelong learning, this is the idea where you have one agent, right? So you have just one agent and it does a bunch of different tasks. So maybe if tasks are blue first, it does like this task, and then it does this task, and then maybe it goes back and does this one. Point being is that it has a long lifetime, maybe forever. You know, even we as humans, right, we have very long lifespans. And over the course of our lives, well, we have to adapt to do many things. Some things we'll forget to make room for new memories, and we always have to be figuring out how to adapt to our surroundings. And what this paper shows is that using backpropagation specifically, well, backprop has this bad property, it turns out, where if you keep trying to do tasks like this, one after the other, after the other, after the other, eventually by the time you get all the way down here, the network is not going to do very well at learning these new tasks. And that's even if you forget previous things, it's still going to do bad on this. It kind of goes like that saying, right? You can't teach an old dog new tricks. And this paper shows a method to overcome that limitation. So I found this to be very interesting because as far as I'm aware, and any of the reviewers in this paper were aware, this is a new phenomenon, this decaying plasticity. So that's what I want to talk about today. We're going to take a look at how they show that this happens, some experiments they run, and then also a way that they propose to overcome this by using randomness in these networks. And just a heads up, I actually happen to know all three of these people that published this paper, so maybe I'll be a little bit biased, maybe not, I don't know. I try to be as objective as possible, but you know, I at least want to let all of you know. Now, the one last thing I'm going to tell you all before we jump into this lovely paper is consider liking the video and subscribing to the channel if you like this type of content. I really appreciate it. And now with that out of the way, let's jump into the paper. So the full name of this paper, as you can probably see, is Continual Backprop, Stochastic Gradient Descent with Persistent Randomness. So what you'll see here is essentially what I just said, right? Backprop performs well initially, but over time, the performance degrades. That is clearly an issue, right? Especially when we want to learn for a long time. So what they do is they propose this algorithm called Continual Backprop, hence the name right here. Now, this might be a little bit of a misnomer. What they really do is they're just randomly initializing weights, right? So continual backprop will be essential where the advantages of random initialization are present throughout the learning. Random initialization, right? Random initialization of weights. Why is that important? This actually wasn't, I think, something that was very clear to me and maybe not very clear in general. And I think this paper does a good job of pointing out why this is actually something that's desirable, which we'll get into as we go. So let's go down a bit. I want to skip past the introduction because I kind of just explain what's going on right here. We have these non-stochastic problems where we're going through lots of different tasks one after the other. And I want to jump into some of the experiments they actually run. And this is one of the strengths of this paper, I would say. Here we go to the non-stationary problems, is that they actually have a lot of very solid experiments they run in many different environments. So the first one they have is, they call this the bit flipping problem. We'll take a look at that in 1 second, but they also have permuted MNIST, which is another type of classification task. This is different from normal MNIST. We'll talk about how in a second. And they also have non-stationary RL problems, so slippery ant and this semi-stationary reacher. And these are all things we will briefly go over. And they're all different environments that shows that this problem that we were talking about, it actually exists within all these environments. So in the bit flipping problem, we have, I think it's like 20 to 30 inputs right here. And these are each bits, like, right, they're just 1 or 0, very simple. And the first half of these bits, or the first set of these bits, these are going to be changing over the course of the training, right? So maybe they'll all start as 1, and then one of them is flipped after 10,000 steps, and then another one is flipped after 10,000 steps, or something like that, right? So the point here, I think it's every 1,000 steps, one of these is flipped. And the other inputs right here are just independently sampled, so they're like random noise, you could think of them, right? So we take this input and we have some target network. So that's what's right here. So let's draw it though. Let's draw the target network. I think it's like, say, 1 or 2 layers. So the target network is something like this. So the input comes into this target network, then it gets fed through here, and we end up predicting some Y. So this Y, it could really be anything. These weights are actually randomly initialized in the target network, and I can draw this here. Target network. And what they're trying to learn here is essentially they're trying to mimic this target network. So there's going to be another network here. So this will be the learned network. That was also supposed to be a rectangle, but oh well. So the input also goes into this learned network, and we output some Y hat, which is what we're predicting the Y to be, right? So this is learned. And the key here is that the learned network, these weights, I drew them smaller intentionally because this learned network is much smaller than the target network. So the target network is pre-initialized to be random and it never changes. So the learned network is essentially trying to learn whatever the target network is doing, but because it's so much bigger, the learned network will never be able to approximate it exactly. Rather, as the distribution changes, the network is going to have to change to adjust, right? Well, after the first, several hundred steps or so, this might be getting this right. Well, remember, every 1,000 steps, one of these bits is going to be flipped, and then this is going to have to be making a new prediction. So it has to sort of adjust. The more these bits flip, the more it will have to change to mimic this target network. That's the bit flipping problem. Hopefully that was an okay explanation. It's really quite a simple problem. Sorry if that wasn't the best explanation. The second thing they use is permuted imness. They don't really have something right here, but if you've ever seen the imness data set, essentially it's these black and white numbers, right? So you'd have like a black square right here. Perfect coloring job, I know. Thank you very much. And then they have within that, I don't have a white right here, but they have some number, right? So there's a handwritten digit. So maybe this one would be 7. Maybe they'd have one that's like 2, another that's 3, another that's 1, and they have 60,000 of these images. The permuted imness data set essentially says every so often, so maybe every 10,000 or 20,000 steps, we can just reorganize these pixels, right? So maybe the first pixel will go here, and this pixel will go to where the first pixel was. I could have drawn that in a different color, right? So they're essentially swapping the places of these pixels. And they can swap any number of pixels, but the thing is, it doesn't swap every single time. It only swaps, say, every single 10,000 steps or so, so the network has a chance to actually learn what's changed. And then the next several problems they use are all reinforcement learning problems. So we have Reacher. This is essentially where this robot right here in the center has 2 joints. So this is joint number 1, joint number 2, and it has to move these to reach over to this dot. Fairly simple enough. Slippery ant is kind of, I guess it's not similar. It's like a robotic task where you have like this ant. It looks kind of like this. It has 4 legs, and it has to walk around on the ground going from start. So we can do like start to finish. So it's just walking from one place to another. And then the final one right here, oh, semi-stationary reacher. We just talked about that one. So what I just described is what those two are. The thing is that in both of these reinforcement learning environments, something's always changing. I forget what it is in the reacher one, but at least in the slippery ant one, the ground itself is actually slippery, like the friction is changing. So that level of friction is constantly, not constantly, but every once in a while, it is being changed. So that's why these are non-stationary problems. And remember why this non-stationary is important. It's because we essentially want to see if the network can learn even as things change over a long course of time. If it keeps changing forever, will the network keep being able to adapt forever? And then in here, they specify the details, right? Like what I said right here, right? 10 million time steps is the friction changes after every 10 million time steps. So you see the network has, in all these cases, a very long amount of time to readjust to the new parameters. So it's not like it's just showing it a new thing, a new setting for 10 steps and then having it, try and adjust. It gives it a good amount of time. And now that you hopefully get a rough idea of what these environments look like, we can take a look at some of the earlier results. So let's scroll in here and go down. What I want to take a look at now are these two graphs right here. And these are fairly simple. Essentially, this is going back to the bit flipping problem we were just talking about, and it's just showing the online squared error, so the training error. And what you'll notice is that over time, the error actually goes up. The error actually goes up in all these cases. The difference between these, by the way, is the activation function, a tan H versus a relu. Honestly, I don't know why they look both at it. But the important thing here is no matter what the step size, no matter what functions they use here, why does the error rate go up? And the thing is, it actually does go down at first. It just goes down very quickly. You'll see that this is over 1 million steps is what we're looking at, right? So it actually does go down. This is just such a large time scale you actually can't see the downwards trend in most of these. But then after that, it starts going up. And that's this phenomenon that we were talking about, right? This decaying plasticity. So it's very interesting. Why does this happen? I think this 5th time I've asked that question. Well, we're going to get into that, but let's go through a few more of these experiments to show you that this isn't just an issue with the bit flipping problem. This is actually an issue with all of these, although to a different degree in all of them. So if we scroll down, the next thing we can take a look at is right here. So this is now the permuted imness. Remember, so this is classification of handwritten digit images. And you'll see a very similar thing here. At first, the online classification accuracy starts off fairly low. And I say fairly low, it's like the low 90s, but that is low for MNIST. And over the course of 12 million samples shown, this goes up, but then it starts to go down again, right? It goes down. And no matter what the step size, again, it gets worse. And this is kind of weird, right? The accuracy should be going, I mean, maybe not up over time because the problem is constantly changing, but we would hope that it would be steady. We'd hope it would go to like, say, 95% and just stay there for the rest of the time instead of having this drop. Now, I will mention, you probably noticed that these numbers on the left here, 95, 94% accuracy, this is all within like 2 percentage points on INMIS. And that's just one thing I don't love about INMIS, the fact that it works over such a small number, a small range. I guess at the end of the day, if the standard deviations are very small, it should be fine, but it does bug me a little bit, not gonna lie. So sorry, now I'm gonna ask the same question one more time, but maybe now actually give a hypothesis. Why is the accuracy going down in all these cases? Well, they give a hypothesis here, and this hypothesis has to do with these small random weights. And what they point out is that at the beginning of all this training, well, these weights were distributed in a way that they were very small and they had some sort of random distribution, right? After learning for a while though, they have become optimized to reduce the error, as they point out here. Hence, once the next problem comes around, or essentially the pixels have been permuted in some way, that's a new problem now that this has to solve, but the weights are no longer those small random weights. They're probably a bit bigger because they've been pushed in a direction by backpropagation, and there might be some properties of that initial weight distribution that must have some special properties, they say, that allow for the learning network to adapt fast is the key here. So this initial distribution, what those properties might be, it could be, they point out a few things that it could be, right? Like this diversity of features or non-saturated features, which is essentially where some features stop contributing, or maybe it's just the fact that they're small. There's all these things that they hypothesize. They actually do test these to some extent, and we'll be looking at those results soon, but that's the idea. So how can we solve this then? Well, a very simple solution is if small randomly distributed weights work well in adapting, well, why don't we just give the network some of those every once in a while by resetting the weights that are not contributing to the network? And that's what they do. It's a fairly simple idea, and we are going to kind of look at how they decide what weights are not contributing and what to reset and how frequently. There's not too much math in this paper. This is probably all we're going to see down here, which I think is kind of nice. I like the simplicity of this method. The full formula they use for resetting the weights or deciding which weights to reset is down here, and they slowly build on this, right? So first they have what they call the C variable, I believe is the contribution utility, I think is what they call it. And H is the hidden output right here. And W is just the weights from this current layer to the next layer. So it would be like this, right? This, and this in this case, if this H is a hidden unit. So you can see the larger each of these are, well, the larger this contribution utility is going to be. It's quite simply how much this hidden unit is contributing in this layer, how much it is outputting, like how big its outputs are. And then they do a minor change here. They essentially, you'll see they adopt this here and they just make this small change, add this F term, and this is essentially just correcting for the mean, nothing too major. So that's the contribution utility. And then the other thing they point out is this adaptation utility. And it is the inverse of the average magnitude of the feature input weights. Well, why does that matter? First of all, this contribution utility, I should say, this one matters, the Z right here. This matters because if something has a large weight, it's probably going to be contributing a lot. And we don't want to get weights, rid of weights that are contributing a lot. If it's doing well, or at least it is helping decide the output, it's probably important. Let's not mess with it. And then adaptation utility says, well, if these weights are small, if the input weights are small, that's a good thing. By resetting the inputs to this, we can easily change this and it can be adapted. So it's not like, so to say, saturated. So when you combine those two things together, you get the equation for U down here, which is the total utility. Again, this is just literally the multiplication of the two that I mentioned before. And it's a measure of how much a single hidden unit, or they call it feature in this paper, how much it contributes to the outcome, right? Or at least the outcome in that specific layer. So what we want to do is they should have an algorithm down here. Yep, so let's go through this step by step. It's actually fairly simple. You start out by initializing a few things. I wouldn't worry about that, but you initialize your input. So you do a forward pass. This is pretty standard. You evaluate, you receive your loss, you do a backwards pass. So this is like your normal training loop, right? Forward pass, calculate the loss, do a backward, if you're using PyTorch, you zero out the gradients, you you use your optimizer, whether that be Atom or SGD, and that's all pretty normal. This is the part that is new. For each layer, what they do is they first update the age of a node. Why does this age matter? And A is the age here. Well, the age matters because once they reset a node, it's probably not going to be contributing very much immediately. So they want to give it some time for it to mature before they just reset it again, right? So what they then do is they calculate the utilities. Equation 5 is the equation we just looked at. So they calculate the utilities for each node. Then they find the eligible feature vectors. Eligible feature vectors are essentially just ones that are old enough. And then they choose a certain number of features. And this is a hyperparameter right here. This P is essentially how many are being chosen. And what they do is for the ones with the lowest utility, well, they just reset the weights going in and out of that hidden unit. And that's the two steps right here, initialize input weights and output weights. So they reset them. Then they essentially reset some of these tracking variables. I wouldn't really worry about that unless you're implementing this, but that's the idea. It's very simple, right? So they would essentially have some sort of weight like this one up here, this hidden unit right here. They'd have this hidden unit. And if this one's not contributing much, well, this and all of these would just be reset to however they were originally initialized. And what they show is that this actually works fairly well. So let's go ahead and take a look at some of the experiments they ran to see how this works in practice. This figure 6, these graphs are the first ones I want to take a look at. The only difference between these two, again, are the tanh and ReLU. I don't know why I guess maybe tanh is common for some of these problems is why they use them. I'm not sure. But either way, the results for both are somewhat similar. And what we'll see is that CBP right here is continual backprop. This is their method. And on the y-axis, we have the online squared error. Oh, it's kind of hard to highlight vertically like this, but we have the online squared error. So the lower this is, the better. And what you'll see is that in both of these cases, continual backprop, their method, performs fairly well. More specifically, though, it is consistent, right? It doesn't go down, it doesn't go up, it stays relatively steady after it learns the initial, whatever it's going to learn, instead of degrading over time. Whereas these other methods, at least most of them, they go up over time. The error goes up as time passes, and this is the same thing we saw before, right? BP is normal backpropagation, and we can see that that performs fairly poorly. L2, however, the L2 is the purple one right here. This is a way, I should write this, L2 is essentially a way of penalizing a model for having too large weights. So if we have a weight and it grows and it grows and it grows, well, the more it grows, the more the loss is going to go up. It essentially just adds an extra loss term for that. And because of that, the weights should ideally stay small, right? We should stay with these small weights, which is what the authors of this paper theorized is at least one of the reasons why continual backprop works well, or one of the reasons why these don't work well. And we can see that that's probably partially true because L2, this L2 term does actually help. Very clearly, it's doing better than backprop. And in this case with the tanh activation function right here, it's actually doing about the same as CBP. They also do a quick parameter search and find roughly the same thing. CBP and L2 are definitely doing the best. CBP definitely better with ReLU, and roughly the same when you use the tanh activation function. So looking at results like this, it does make you think maybe the issue is just these small weights. Heading down to the next figure they have right here, it's essentially the same graph as what we saw before, except for this time it's with permuted MNIST. You can see that backpropagation, the accuracy goes down. At first it goes up, but then it goes down. Dang, I really hate how OneNote is doing that. I wonder if I can turn that off. You'll notice the online norm does do better initially, but it also goes down as time progresses. I should raise that so you can actually see. The CBP though, and I'll zoom in a little bit for you all, what you'll see is that it stays very consistent. Even if it's not the best the entire time, it doesn't go down very much over time. And that's because, or I mean, that's kind of the whole point. That's what we wanted, right? Even if it's not the best, it's doing, I mean, by the end of it, it's doing the best because everything else decays over time. And I know I already mentioned this earlier, but you should be a little bit wary of this. Note that this is all within like 1 percentage point on this task, which again, I don't love MNIST because of that, but at least they do have not error bars here, but the things where they're filling in their shading to show the either standard error or something, and it looks very small, so this should be statistically significant. So we can see that this is the case for both of these supervised learning problems now, and you might be thinking, as I pointed out, maybe this is because the weights are small. The weights being small is important so that the network can adjust. So the next experiment actually, interestingly enough, takes a look at this. So this figure 8 right here. And what it looks at, figure 8, is the evolution of the mean magnitude of the weights. And what you'll see is that backpropagation expectedly is going up quite a bit. The magnitude of the weights goes up as you train more and more. L2 and CBP, they both stay low though, yet CBP is still outperforming L2, at least in most cases. So why could that be? I don't know. It's interesting. It's an interesting experiment that shows that maybe the small weights are not the only thing, at least. Maybe they're one factor, but even if they are a factor, they're certainly not the whole picture. So this is still somewhat a mystery. Very quickly, we can also go over the graphs here. What this is these are the slippery ant and the semi-stationary reacher. Remember, these were the reinforcement learning problems we were talking about, and they use PPO, which is a very standard algorithm in reinforcement learning that works fairly well typically on both of these problems. And what you'll see is essentially what we saw before. Standard methods, the standard PPO, which uses normal backpropagation, it degrades very quickly. In contrast, while we do have these very clear divots in performance every time we switch the friction of the floor, at the very least, continual PPO, which is their version, they're using their version of backprop, and the L2 version, although not quite as good, they both do a lot better in keeping up than this standard PPO. In the semi-stationary reacher, honestly, I'm not entirely as bought into this one. They all really are decreasing quite a bit. Like, sure, continual PPO and PPO with L2 do better, but these are also very, very noisy curves. So I do wonder, yeah, I'm not buying this one, but I do think the slippery ant one is much more convincing. But these are roughly what we were seeing before, right? Continual PPO looks a little bit better, maybe, although maybe L2 is roughly the same. It's hard to say just from these. So those are really the takeaways from the main paper. And then that's kind of what they covered in the main paper, right? First, we looked at this decaying plasticity issue. And once it was pointed out, they proposed this continual backprop method to help fix this. One thing that, and this is one thing that the reviewers pointed out, maybe why this paper wasn't accepted, is that you kind of wish they dive into this issue of decaying plasticity more, right? Just based off the last graph, we could see that the weights being small is not the only issue here. And they actually did add an appendix. So we're going to scroll down quite a bit. And I think lots of these were at the request of the reviewers. And they actually pushed them to do some very interesting experiments. So sorry for the scroll. Let's go down, go down. Okay, and here we are. The next thing we're going to look at is this figure 18. So this is, again, an experiment on the permuted imness data set. And what you'll actually see is that depending, so there's over 20 million examples, depending on how frequently the task was switched. So here it was switched every 10K episodes. Some pixels were permuted. Here every 100K episodes or 1 million episodes. Well, that actually changes how well the network is able to adjust. So you can see after 10K, or if you do it every 10K, it just absolutely does terribly. But the more time you give it to learn each one, the better it does. And in one hand, this should be like kind of obvious, you'd think, right? You give it more time to adjust, okay, sure. But at the same time, this might not be obvious because you are training for the same amount of steps. And at every step, all the weights should be being updated, right? So I'm curious why exactly this is the case. I haven't thought too much about this, but I thought the results were nevertheless interesting. The next thing that I want to point out, and this looks more into exactly why plasticity decay happens, is this idea of saturated features. They point this out in the paper. And what they do is they define, I think it's up here where they define, yeah. So we call a feature is saturated when the magnitude of its output is more than 0.9, essentially when it gets too big. And I believe the reason they do this is that once it gets too big, it's going to be like very hard to change what it's learning. It's like kind of saddled in, it's at a, I'm not sure, saddle point is probably a word for something else, but that's what they call a saturated feature. And what they point out is that with normal backpropagation, almost 90% of the features are saturated. Interesting. And you can see that here, right? So here we have backpropagation. You can see it reaches this 90% threshold. CBP is actually also fairly high at around like 0.6 or so. L2 is after that at around like, what's that, like 0.4. And then online norm is here with like 0.2. So interestingly enough, I've just destroyed this graph. I should stop using highlights on the graphs. So we can actually see that having features saturated might not be the biggest issue, at least not entirely, because CBP has the second most number of saturated features after backpropagation, even though like CBP is doing the best in most of these cases, right? And online norm is usually not doing very well in these, yet it still has a very low number of saturated features. So as it turns out, maybe features being saturated isn't a huge deal. And then this other thing they point out here is the magnitude of the gradients, trying to see if that has any correlation. And what you'll notice again here is that it doesn't seem to have a correlation, right? These are in a completely random order, it seems. Backpropagation has the smallest magnitude. CBP has the second smallest magnitude. Even though it performs the best, it's like in between these methods that also perform fairly well and these methods that perform very poorly. So as it turns out, maybe neither of these things have to do with plasticity decay. It's really hard to say. And it would be interesting if they went into more detail on this. I think I just mentioned this, but that probably is one of the reasons this paper didn't actually get accepted, is because this probably, I would agree with what the reviewers were saying, which is this is probably the most interesting part of the paper, right? This new phenomenon. And we still don't really know why it's happening. There's this idea that having some initial distribution of small weights is important, but that doesn't seem to be the whole picture. And neither of these seem to be showing anything more helpful. So it really is an open question. And I'd be very curious to see any future work that looks into this. In conclusion to all of this, it looks like, the main contribution I thought of this paper was this decaying plasticity, interesting issue, and of course, the method they propose. It really is, at the end of the day, this really exactly fit this idea of you can't teach an old dog new tricks, right? Once the network learns so much, it can't learn anymore, which is definitely not a great thing when we want to learn over long horizons. One thing they also mentioned in this conclusion that I think it would be an interesting direction is the fact that this is based on heuristics, right? When they drop a node or reset it is very much based on heuristics, and it would be very interesting to see if they remove that limitation, maybe meta-learned what heuristics to use. Maybe the results would be a little bit different, better. I have no clue. I'd be very interesting to see that. But anyway, that is Continual Backprop in a nutshell. I hope you enjoyed this. If you do, I do a whole lot of things like this on the channel, so do consider subscribing. Anyway, thank you so much for watching, and I hope to catch you all next time.